Magsys, and we're designing an electrically regenerative suspension system. We're using air springs to allow us to control the spring rate, and we're using a linear generator that allows us to control the damping factor. These together allow us to build a green performance suspension system.
First, we'll discuss the engineering requirements, which are required to define the project. Not only do they provide constraints on the system, but they also allow us to test it, thus ensuring accountability.
Then our presentation will be talking about our block diagram, which will contain 12 blocks, and they are linear generator, current regulator, DC to DC converter, voltage regulator, code display, accelerometer, microcontroller, pressure sensor, air solenoid, air spring, air reservoir. And then we'll be talking about our unique design concept, and then our timeline, and lastly will be our conclusion. In our engineering requirement, we'll start with the power generation. The system will have less than 10 watts at any given time. Also, the system will have resonant frequency between 1 and 2 Hertz.
The system will be convenient for the user. This means that the spring and damper assembly will have a volume less than 150% times the OEM standard shock. This also means that the onboard electronics will occupy a space less than 64 cubic inches.
Our system will also have controlled suspension behavior. It will have no more than 10 moving parts and will fail in an undamped, which is to say zero damping manner.
The system will be monitored. That means it will monitor the damper voltage output within plus or minus 1 volt in less than 5 milliseconds. It will also respond to user input in less than 1 second.
Our system at the top level will take in necessary environmental effects, battery power, user input, and air pressure to pressurize the air reservoir. Also, it will output force and pressure on the ground to supply light and electrical power. In our block diagram, we will start with the voltage regulator. The voltage regulator will be powered with a vehicle battery of 12 volt. Also, it will adapt power from the vehicle voltage to load the voltage equipment. And another reason of having the voltage regulator will be to prevent the microcontroller and the sensor from getting burned. The current regulator block will turn AC voltage output from linear generator to a DC voltage. Also, it will limit the flow of electricity to change how stiff linear generator feels. As you can see in the block diagram, the current regulator feeds DC filter electricity to microcontroller for monitoring. The DC to DC converter block will convert a large voltage from linear generator to a small voltage to charge the battery. The DC to DC converter will also be using a pulse from microcontroller. In this block, we'll be using accelerometer to measure the acceleration of the system. Also, we'll be using sensor to tell microcontroller how fast the wheel is moving vertically.
Alright, our linear generator is a stack of coils wrapped around a magnetic core with steel spacers in it that directs magnetic flux outward instead of upward and downward in line with the magnetic stack. We're going to have magnets laminated north to north with a spacer in between that focuses the flux outward instead of in line with the magnets. This will convert vibration in the road into electrical energy, which then we can throttle, allowing us to adjust the stiffness and also the energy regenerated from this damper. Our pressure sensors are basically just going to be sensors that tell the microcontroller how much air is in the spring, and from this we can determine how stiff the spring is and what the spring rate is in our air spring. We're going to have two air solenoids. One of them is coming from the air reservoir into the spring, and one is going from the spring out to the environment. This allows us to let pressure in or out of the spring and also bleed pressure from the spring out to the environment and decrease our spring rate if needed. Our air spring is a pneumatic cylinder that uses air pressure to create a spring constant. The air pressure on the back of the piston and the cylinder acts as a spring when you push against the cylinder, and this allows us to make an adjustable spring rate to make the wheels move faster if the wheel experiences a dip in the road, or if we use a softer spring rate, it allows the wheels to react faster to bumps in the road.
The microcontroller is the brains of the system. It controls the current and output voltage by sending pulse width modulated signals to the current regulator and DC to DC converter. It reads outputs from sensors and also reads inputs from user controls. It will be used to control information sent to the display and will adjust spring pressure. The code tells the microcontroller how to manage everything. It will be written in C and then compiled and used to program the microcontroller. The display will show user settings as well as information gleaned from sensors. The information will be put on the display by the microcontroller. The air reservoir consists of a pressurized air tank, which allows air to be forced into the springs. Finally, the air spring, linear generator, and accelerometer will be mechanically coupled.
Our design has several unique design considerations. First, we have a linear generator for a suspension damper. This is a new technology with few experts in it and is primarily used in wave generation. Second, we're using air springs for our suspension. These are relatively expensive because of their relative complexity, and they require good seals. However, they are incredibly lightweight, which makes them ideal for performance vehicles. Third, we're using current throttling. This allows us to precisely adjust our damping factor, and it allows us greater control over the current coming out of the generator. However, it does add considerable complexity to our control system.
For term week 8, we'll deliver our presentation. Also, we'll select customer and engineer requirement. We'll create pass-fail test based on our requirement. By week 9, we'll deliver at least 3 blocks diagram and produce electronic schematic. By week 10, we'll deliver our final project specification. Winter break, we'll start building our mechanical system, and winter term week 1, we'll start ordering part, and by week 2, we will start building the part. By week 5, hopefully the whole part will be built, and by week 6, we will do the individual testing, and by week 8, we'll do the subsystem testing. And last week, week 10, we will do the final project testing.
To recap, our project consists of an electrically regenerative suspension system. It is unique in that it uses a linear generator as a damper. It also employs pressure-controlled air springs and is electronically controlled.